Hello students, we are dealing the chapter wave optics and we saw some of the topics in our previous class. Now today we will see some more topics. Here we have first topic as superposition principle. When two waves of displacements y1 and y2 when superimposes with each other, we get the resultant displacement of the wave. Now the superposition principle states that the resultant displacement of the light wave when two light waves having the displacement y1 and y2 superimposes with each other, then the resultant displacement will be equal to vector sum of the displacements of individual waves. Now let us see that. Here we have one of the wave y1 which is given by y1 is equal to a1 sin omega t. Now second one y2 is given whose amplitude a2, so this equation can be represented as y2 is equal to a2 sin omega t, or if any phase is there then you can take phase as pi. Now the law says or the rule says that the vector sum of these two displacements, that is first wave we have here whose equation is given by displacement equation is given by y1 is equal to a1 sin omega t. For second case the displacement equation is given by y2 is equal to a2 sin omega t plus pi, having the amplitude a1 and a2. When these two waves superposes with each other, we will get the resultant wave which will be shown here. So this graph shows that the resultant wave have the displacement which is sum of the displacements of both the waves, and amplitude will be equal to sum of the amplitudes of both the wave. Now if we say these two waves, both the waves are in same phase, that's why addition of these two waves, I mean the amplitude of both the waves when we add will get increases. Now come back to the second case. Here also the graphical representation of wave displacement is similar to the previous one, but the displacement, I mean the amplitude of the wave is negative here, it is in the downward direction. Similarly for second wave also it is in downward direction. When both the waves are added together, their amplitude get adds, but that will comes out to be in negative direction instead of positive direction. Here also we see that amplitude increases. Now see the third case. Here the wave graph is shown here. For first one, amplitude a1 shows in upward direction. For second half the amplitude is shown in downward direction, and the second wave displacement is shown in the graph which is just opposite to the first one. That means second displacement or the phase is just opposite to the phase of the first one. When we add these two, we get the amplitudes as a1 minus a2. a1 minus a2. If a1 is equal to a2, then the resultant displacement, the resultant amplitude of the wave comes out to be 0 in this case. As a result, we cannot see any ups and down. Instead we will see a straight line graph that indicates standing waves. So this shows that when two waves having the same amplitude, but if they are in out of phase, the sum gives standing waves. So finally we can say that superposition principle states that the resultant displacement of wave combination will be equal to sum of the vector addition of displacements of each individual waves. Here we can see first wave having the displacement y1 combines with second wave having the displacement y2, and finally we are getting a separate single wave which have a displacement y, and at the same time it will also have the phase difference compared to y1 and y2. Here the considered phase between y1 and y2 is pi. So pi is nothing but it represents, it is said to be as phase difference. Phase difference is the factor which determines the position and direction of the particle at a particular instant of time with respect to original point. Here omega t plus pi represent phase of the particle corresponding to wave displacement y2, which represents the direction and position of the particle at particular instant of time compared to initial time. Now if we take the wave equation for one of the wave as y1 is equal to a1 sin omega t, and for other y2 is equal to a2 sin omega t plus pi, then according to superposition principle the resultant displacement y will be equal to y1 plus y2, which is equal to a1 sin omega t plus a2 sin omega t plus pi. Now the remaining derivation of this one we will see in the case of interference of wave in our next topic. Now we will see the next topic, interference of waves. The name interference of waves states that it is the phenomenon which represents that the final energy is due to the redistribution of energy of the individual waves. Suppose that if we take the displacement equation for first wave as y1 is equal to a1 sin omega t, and y2 for the second wave y2 is equal to a2 sin omega t plus pi, where phi is the phase difference between first wave as well as second wave. Let us suppose that first wave is represented graphically like this, which varies with time t, having the displacement a1, having the amplitude a1 and displacement y1. Second wave is represented by the amplitude a2 and displacement y2, which is given by like this. Now when these two waves superimposes with each other, their energy get redistributes and we will get the redistribution of energy at the screen. So interference of waves states that when two waves having the displacements y1 and y2 superimposes with each other, then we will get bright and dark bands on the screen, which is due to the redistribution of energy of the individual waves. So the phenomenon of redistribution of energy of the individual waves to give maximas and minimas on the screen is said to be as interference of waves. Now we will find out the derivation for this. Here according to superposition principle, y will be equal to y1 plus y2. The value of y1, which is a1 sin omega t, can be substituted here, a1 sin omega t plus y2 is a2 sin omega t plus pi. So here we can write a2 sin omega t plus pi. Now a1 sin omega t plus a2 sin omega t plus pi can be expanded by the formula sin a plus b, which is equal to sin a cos b plus cos a sin b. Using that formula, sin omega t plus pi can be written as sin omega t cos pi plus cos omega t sin pi. Now further in the next step we can write a1 sin omega t plus multiply this a2 with the factors whatever present inside the bracket. We get a2 sin omega t cos pi plus a2 cos omega t sin pi. Now from first part, that is a1 sin omega t and a2 sin omega t cos pi, that is from second part, we can take sin omega t as a common factor. On taking sin omega t as common factor, we get a1 plus a2 cos pi. In the outside we can write sin omega t plus a2 cos omega t sin pi. So as I told you in the superposition principle that the resultant displacement is the vector sum of individual displacements of the wave. So this can be represented in terms of vector diagram, that is here suppose that we have the displacement y1, this one has the displacement y2, then the resultant displacement will be y, which makes some angle theta with the displacement y1. So the resultant displacement y will have phase difference of a theta with reference to y1. The angle between, that is the phase difference between y2 and y1, can be taken as pi. So here we get final displacement y is equal to a1 plus a2 cos pi bracket sin omega t plus a2 cos omega t sin phi. Now let us take, let a1 plus a2 cos pi is equal to, we can take a cos theta, where a is the final displacement of the wave after recombination, that is when both the waves are combined together, we get final displacement a. So here a1 plus a2 cos pi is taken as a cos theta, and take a2 sin pi as equal to a sin theta. Now substitute the value of a1 plus a2 cos pi equal to a cos theta, and a2 sin pi is equal to a sin theta in equation 1. So the equation becomes y is equal to a cos theta multiplied by sin omega t, plus in place of a2 sin pi we can take a sin theta. So a sin theta cos omega t. Now the value of a1 plus a2 cos pi is equal to a cos theta and a2 sin pi is equal to a sin theta is taken to convert the given expression in terms of sine angle, sine of phase angle, so that we can compare the resultant amplitude as well as phase with the original wave equations. So here from this expression you can take a as common. Taking a as common, we get in the inside sin omega t plus sin omega t cos theta plus cos omega t sin theta. Now further this can be written as sin omega t plus theta using sin a plus b formula, that is sin a plus b is equal to sin a cos b plus cos a sin b. So further this can be written as y is equal to a bracket sin omega t plus theta, equation 2. Now when we compare this equation 2 with the original equation, that is equation A and equation B, we find that the resultant amplitude is something different from the amplitudes of the individual waves at the same time, and the resultant wave will have a phase difference of theta compared to the phase difference of both the waves. Now here the derived resultant displacement is y equal to a sin omega t plus pi theta. So where theta is the final displacement, where theta is the final phase between compared to initial waves, the resultant displacement here is y is equal to a sin omega t plus theta. Theta can be determined by using parallelogram of law of addition of vectors. So the resultant phase angle is given by tan theta is equal to a2 sin pi divided by a1 plus a2 cos pi. The resultant phase will also depends upon the phase difference between the initial phase difference between y1 as well as y2. Now let us find out the intensity etc. Here we have a1 plus a2 cos pi is equal to a cos theta and a2 sin pi is equal to a sin theta. Now let us try to find out the resultant amplitude. So for resultant amplitude, square both these parts, that is let us say this equation as 3 and this one as 4. Square and add the equations 3 and 4, we get a square cos square theta plus a square sin square theta is equal to a1 plus a2 cos pi whole square plus a2 sin pi whole square. Now from this one you can take a square as a common factor. So taking a square as common factor, we have cos square theta plus sin square theta bracket close. On the other side, expand this using a plus b whole square formula, you get a1 square plus a2 square cos square pi plus 2a1 a2 cos pi plus a2 square sin square pi. Now from a2 square cos square pi and then a2 square sin square pi, you can take a2 square as common factor. Taking that as a common factor, you will get a1 square plus a2 square cos square pi plus sin square pi plus 2a1 a2 cos pi. Now we know that cos square pi plus sin square pi is 1. So finally you get a1 square plus a2 square plus 2a1 a2 cos pi. On the other side, again here also cos square theta plus sin square theta is 1. So finally you get a square is equal to a1 square plus a2 square plus 2a1 a2 cos pi, where a square is the amplitude of the resultant wave, a1 is the amplitude of the initial wave, and a2 is also the amplitude of the second wave, which are superimposing with the first wave, and pi is the phase difference between the initial superposing waves. Now we know that, let this as equation 5, we know that intensity is proportional to a square. So here a square can be taken as I. So I will be equal to, here it is I1 square plus a1 square plus a2 square plus 2a1 a2 cos pi. Let this as equation 4. Now as I told you that I is proportional to a square, therefore this a1 square can also be written as I. So I will be equal to, here it is I1 plus I2, whereas I1 is proportional to a1 square, I2 is proportional to a2 square, and the proportionality constant on both sides get cancelled out. So directly we can write instead of a square as I. So here this can be written as 2 under root a1 whole square, here also under root a2 whole square cos pi. Further this can be written as, in place of a square we can write I, in place of a1 square I1, in place of a2 square as I2, and then a1 can be written as root of a1 square. Similarly a2 can also be written as root of a2 square cos pi. Now we know that intensity of the first wave is directly proportional to the square of amplitude. So here you can write intensity of the first wave I1 plus I2 plus 2 I1 under root second I2 cos pi. So this is the intensity of the final wave obtained when two waves superimposes with each other, and again that will depend upon the phase difference between two waves. Similarly, the amplitude square is equal to a1 square plus a2 square plus 2a1 a2 cos pi. Now let us see the maximum as well as minimum intensity. So first we have here a square is equal to maximum and minimum intensity. Here we have a square is equal to a1 square plus a2 square plus 2a1 a2 cos phi. The amplitude will be maximum if pi is equal to 0 degree or cos pi is equal to 1. For maximum intensity, cos pi is equal to 1. So we get a square is equal to a1 square plus a2 square plus 2a1 a2 multiplied by 1, and also a square means it is proportional to I, therefore in place of a square we can write I maximum is equal to a1 square plus a2 square plus 2a1 a2. Further this can be written as a1 plus a2 whole square, that is a1 plus a2 whole square. When we expand, you will get this expression. So I maximum is equal to a1 plus a2. Similarly, for minimum intensity, cos phi will be equal to minus 1. This can be possible if pi is equal to pi, 3 pi, 5 pi and so on. For cos pi is equal to 1, pi will be equal to 0, 2 pi, 4 pi and so on. So the minimum intensity we will get as I minima is equal to a1 square plus a2 square plus 2a1 a2 multiplied by the value of cos pi here it should be minus 1. So we can substitute here as minus 1. We get I minimum is equal to a1 square plus a2 square minus 2a1 a2. So further this can be combined in a1 minus a2 whole square form using identity. You get minimum intensity is equal to a1 minus a2 whole square. Now let us compare the maximum intensity as well as minimum intensity when two waves, light waves superimposes with each other. The maximum intensity is given by a1 plus a2 whole square, that will depend upon the amplitudes of both the waves. More the amplitude, more will be the intensity, and minimum intensity depends upon again the amplitudes, but there will be minus sign between these two. Now let us add these two, you get I maximum plus, or let us compare the ratios of intensities. I maximum by I minimum is equal to a1 plus a2 whole square divided by a1 minus a2 whole square. Now divide this by a2, we get a1 by a2 plus 1 divided by a1 by a2 minus 1 whole square. Here a1 by a2 is said to be as amplification ratio, that is the ratio of amplitudes of both the waves is treated to be as R. So in place of a1 by a2 we can write R. So you get the ratios of maximum intensity as well as minimum intensity comes out to be R plus 1 divided by R minus 1 whole square. Now further we will find some more relations, that is let us find the value of I maximum plus I minimum. So I maximum plus I minimum will be equal to a1 plus a2 whole square plus a1 minus a2 whole square. So this is what we already derived. So I maximum plus I minimum will be equal to, now expand this by using a plus b whole square formula, you get a1 square plus 2a1 a2 plus a2 square plus a1 square minus 2a1 a2 plus a2 square. Now from here you can cancel 2a1 and a2, so you get like term a1 square and a1 square comes twice, so you can add these two terms. You get 2a1 square plus 2a2 square. So I maximum plus I minimum comes out to be 2 times of a1 square plus a2 square bracket close. Now similarly I maximum minus I minimum is equal to a1 plus a2 whole square minus a1 minus a2 whole square. Now similarly expand this also, we get a1 square plus 2a1 a2 plus a2 square. Now minus under the bracket we have a1 square minus 2a1 a2 plus a2 square. Open the bracket, you get a1 square plus 2a1 a2 plus a2 square minus a1 square plus 2a1 a2 minus a2 square. Now some factors can be cancelled here, some terms can be cancelled, a1 square cancel out, and then a2 square also cancels. You get 4 a1 a2. Now take the ratios, you get I max plus I minimum divided by I max minus I minimum equal to 2 a1 square plus a2 square divided by 4 a1 a2. 2 to get cancelled out, you get a1 square plus a2 square divided by 2 a1 a2. So these are the ratios between a maximum plus a minimum and I max minus I minimum, which is equal to a1 square plus a2 square divided by 2 a1 a2. Now let us see the constructive and destructive interference. Constructive interference is that interference in which brightness will be there, that means illumination will be there when two waves combines together. Suppose that here you have first wave and this one is second wave. When these two waves combine together, we get bright and dark bands, or we get several bands. Out of that band, the bright band, whatever you get on the screen, is said to be as constructive interference. That means if both the waves are in same phase, when these two waves combine together, we get maximum intensity, maximum amplitude. That maximum intensity and maximum amplitude corresponds to interference fringe, which is said to be as constructive interference. So for constructive interference, the amplitude must be maximum or the intensity must be maximum. For that purpose, cos phi must be equal to 1 or pi equal to 0, 2 pi, 4 pi, dot 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 2n pi. So for the condition phase difference between two waves if equal to 2n pi, we will get constructive interference. So condition for constructive interference is 2n pi. So path difference for constructive interference will be equal to lambda by 2 pi multiplied by phase difference, which is equal to lambda by 2 pi multiplied by 2n pi. Pi cancel, 2 cancel. So n lambda is the condition for constructive interference. Once again, constructive interference is that interference which is obtained as maximum brightness. So this maximum brightness is possible only when two waves are travelling in same phase difference. That means if the phase difference of both the waves are in same phase, then the amplitude of the resultant wave will be the sum of the amplitudes of both the wave. That means the resultant amplitude will increases and the resultant intensity will increases. So brightness will be more than the brightness of individual waves which is obtained on the screen in the form of fringes. So condition for constructive interference is either phase difference is equal to 2n phi or path difference is equal to n lambda. Now we will see the destructive interference. Next, destructive interference. So destructive interference, in the case of destructive interference, if the waves are in opposite phase, when they combines together, the resultant intensity and the displacement comes out to be minimum. So that minimum brightness is said to be as destructive interference. So for destructive interference, the amplitude must be lower than the amplitudes of the individual waves and intensity is also less than the intensity of both the waves. So amplitude here will be equal to a1 square plus a2 square minus 2a1 a2 under root, or in other word you can say cos pi is equal to minus 1. So for the case cos pi is equal to minus 1, pi will be equal to pi 3 pi 5 pi dot 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 2n minus 1 pi. So for the case of a phase difference which is equal to pi 3 pi 5 pi dot dot 2n minus 1 pi or odd integral multiples of pi value, you will get cos pi is equal to -1 and the intensity will be minimum and you will get dark fringe or the minimum intensity fringe. So phase difference for minima or destructive interference is given by 2n minus 1 pi and path difference is equal to lambda by 2 pi multiplied by 2n minus 1 pi, pi get cancelled out, you get 2n minus 1 lambda by 2. So this is the condition for destructive interference. So path difference is equal to 2n minus 1 lambda by 2, that is bracket multiplied by lambda by 2. If the path difference is like this, then you will get destructive interference. We will see the leftover topics in our next class. Till then, try your level best. Thank you.